Throughout popular imagination and countless textbooks, herbivorous dinosaurs have often been portrayed as peaceful, lumbering giants, grazing quietly on prehistoric plants, defenseless and passive in the face of fearsome, carnivorous predators that ruled the Mesozoic landscapes. This portrayal, though comforting and poetic, is an oversimplification of the complex realities these creatures actually faced and embodied. To truly appreciate the dynamic roles herbivorous dinosaurs played in their ecosystems, it is critical to move beyond the stereotype of gentle giants and recognize their potential for danger, defense, and even aggression. The term herbivore itself, meaning an animal that primarily consumes plants, carries with it a subconscious association with benign behavior. Herbivores, in the minds of many, are peaceful. They eat grass, leaves, and fruits, and avoid conflict whenever possible. This perspective, however, largely stems from observing many modern herbivores, such as deer or elephants, which, while mostly passive, can defend themselves fiercely when threatened. But the ancient world of the dinosaurs was not just a simpler version of the natural world today. It was a stage filled with evolutionary pressures, survival challenges, and an arms race that forced herbivorous dinosaurs to become something far more formidable than their gentle reputation suggests. The image of the iconic Triceratops with its 3 horns, or the armored ankylosaurus with its bony club tail, serves as an early hint that herbivores were far from defenseless. These adaptations were biological statements of power and defense, evidence of a lifestyle that required confronting danger rather than merely evading it. Far more than static victims, these dinosaurs carried specialized weapons and armor evolved over millions of years, which indicate a capacity not just for survival, but for combat. Understanding herbivorous dinosaurs means appreciating the evolutionary context of their existence. The Mesozoic era, the age of dinosaurs, spanning approximately 180 million years, was an era of large predators and fierce competition for resources. This meant that herbivores were under constant threat from carnivorous dinosaurs. Predation pressures led to the evolutionary development of defensive traits that could also be used offensively when necessary. Whether it was the spiked tails of stegosaurs, the imposing frills and horns of ceratopsians, or the sheer size and bulk of colossal sauropods, herbivores were formidable participants in the struggle for survival. Moreover, social behaviors, including herding, territorial defense, and parental care, further complicate the simplistic view of dinosaurs as solitary and docile. Many herbivores lived and moved in groups, creating a collective defense mechanism that would deter or complicate attacks from predators. Aggressive posturing, vocal communication, and coordinated movement suggest an intelligence and behavioral complexity that goes beyond a passive existence. The stereotype of the gentle giant is also perpetuated in popular culture through movies, books, and animations that often depict herbivorous dinosaurs as benevolent characters. This cultural lens, while engaging and emotionally resonant, often omits the scientific realities that show a more nuanced life, one where defense, aggression, and adaptability were vital. Scientific studies increasingly reveal evidence that challenges the notion of peaceful herbivores. Fossilized injuries, healed wounds consistent with combat, and weapon-like anatomy provide clues pointing toward an active, sometimes violent lifestyle. For example, the thick skull domes of pachycephalosaurs hint at behavior akin to headbutting, an aggressive behavior used in contests or defense. Similarly, the presence of sharp claws on therizinosaurs and the robust thumbs of iguanodonts suggest a capacity not merely for feeding, but for fighting when needed. Another aspect of herbivore behavior that dispels the myth of gentleness is their ecological impact. These massive animals shaped their environments through their grazing, browsing, and movement, affecting plant communities and the distribution of nutrients within their habitats. Their sheer size alone made them dangerous to smaller creatures and even to each other during intraspecific competition. This introductory discussion sets the tone for a comprehensive exploration of herbivorous dinosaurs, not as timid victims, but as significant, sometimes dangerous players in their ecosystems. Each subsequent section will delve into the specifics of what dangerous means in this context, whether it be aggressive defense strategies, size, temperament, or ecological influence, and reveal the fascinating adaptations that made these creatures durable survivors in a perilous world. By shedding the myth of the gentle giant, we open up to a richer and more accurate understanding of these prehistoric animals, one that recognizes their complexity, resilience, and the evolutionary narratives etched deep in their bones. As we proceed, prepare to discover the unexpected and remarkable ways that herbivorous dinosaurs mastered the art of survival through danger, defense, and sometimes even offense, standing far beyond the simplistic depictions etched in popular imagination. To embark on an exploration of the most dangerous herbivorous dinosaurs, it is essential first to understand what we mean by dangerous in this particular context. Unlike the common assumption that danger directly equates with predatory aggression and lethal strikes, danger within herbivorous dinosaurs encompasses a wider spectrum of attributes. The defining criteria must include not only physical weaponry and size, but also behavioral temperament and the ecological repercussions their presence and actions had on their world. This multifaceted definition allows us to appreciate their complexity and the subtle ways in which these creatures wielded power. First, let us consider defense. Defense mechanisms in herbivores weren't merely passive attempts to avoid death, but evolved active means to deter or counter attacks, enhancing their survival prospects. These mechanisms ranged from physical structures such as horns, spikes, armored plates, thickened skulls, and tail clubs to behaviors including bluffing displays and aggressive posturing. Defense in herbivorous dinosaurs was often an amalgamation of anatomy and behavior, designed to survive encounters with predatory dinosaurs that were frequently larger and faster hunters. For example, anatomical defenses like the bony tail club of ankylosaurus or the formidable horns of ceratopsians were not ornamental. They were weapons capable of delivering powerful blows to attackers or rivals. Similarly, the long, sharp claws of the therizinosaurs, unusual for herbivores, suggest an evolutionary adaptation purpose-built for defense and perhaps offense when necessary. These physical adaptations reflect an ongoing evolutionary arms race where herbivores needed to keep pace with predator innovations to avoid extinction. Yet, defense is just one piece of the puzzle. Size, or sheer physical bulk, also conferred a form of protection inherently tied to danger. Large body size in herbivorous dinosaurs like the sauropods imposed significant challenges to any potential predator. Magnus-like in stature, species such as Argentinosaurus, with lengths surpassing 30 meters and weights reaching dozens of metric tons, were simply daunting. The enormity itself discouraged attacks, not merely due to difficulty in subduing such mass, but because engaging posed a substantial risk of injury or death, even to the attacking predators. Beyond size and defense lies temperament or behavioral disposition. While fossils provide limited direct evidence of personality, clues drawn from injury patterns, comparative anatomy with modern species, and inferred ecological roles give us glimpses into the likely temperament of these giants. Some herbivores were probably predisposed to aggression or at least assertiveness, defending their young, territory, or resources fiercely. In contemporary ecology, many large herbivores exhibit considerable aggression when threatened. Elephants, rhinos, and buffaloes, for instance, are known to be dangerous in defense of themselves or their herd. It is reasonable to extrapolate similar behaviors in their prehistoric counterparts, where evolutionary pressures demanded no less. Temperament also extends beyond individual responses to threat and into social behaviors such as complex herd dynamics, dominance displays, and territorial disputes. The presence of horns, frills, or crests might have served not only combat purposes, but also social signaling, intimidating rivals or competitors without engaging in direct violence. Aggression in herbivores, therefore, occupied both combative and communicative roles. Ecological impact provides yet another dimension to danger. Herbivores were ecosystem engineers, shaping vegetation, influencing soil composition, and affecting the survival of countless other organisms. Their feeding habits could alter forest compositions, create migration corridors, and even open niches for new species to evolve. Sometimes their dominance or sheer numbers could transform entire landscapes, indirectly influencing predator behaviors and ecosystem stability. Importantly, ecological impact also means that danger wasn't confined to direct physical confrontations. The very presence of large herbivores could discourage predators or rival herbivores through dominance and resource competition. The interplay of these relationships adds complexity to the definition of danger. An herbivore might be less dangerous because it can attack, and more dangerous because it can disrupt or control significant portions of its ecosystem. This broader framework, defense, size, temperament, and ecological influence, allows for nuanced consideration rather than a simplistic ranking based only on aggressive behavior or weaponry. Some herbivores might score high on size but low on aggression. Others might be relatively small but capable of startlingly effective defense or social strategies. For instance, a heavily armored but somewhat passive nodosaurid might deter predators through its tough exterior, while a more nervous yet swift hadrosaur might rely instead on rapid flight and mobbing behavior for safety. When we examine these criteria through the fossil record and modern scientific analysis, a pattern emerges. Danger in herbivorous dinosaurs was not a static label, but a set of adaptable strategies honed by evolutionary pressures. The capacity for defense, imposed by size, shaped by behavior, and amplified by ecological roles, made them formidable entities in their prehistoric worlds. As we progress, this conceptual framework will underpin detailed examinations of various herbivorous dinosaurs. We'll analyze their anatomical features with an eye for defensive capabilities, explore fossil evidence of combat and injury, and interpret behavioral clues derived from both physical evidence and analogies with living animals. This approach enables us not just to catalog dangerous traits, but to understand the intricate balance of survival tactics that herbivores employed. Understanding danger in herbivorous dinosaurs in this way also challenges our preconceived notions and allows us to appreciate the evolutionary ingenuity that shaped their existence. It bridges the gap between paleontological data and behavioral ecology, merging bones with behavior and environment. More than mere victims of fierce predators, these creatures often flipped the narrative, becoming potent defenders, rivals, and influential architects of their ecosystems. In the next stage, we will trace the evolutionary arms race that spurred the development of these defensive adaptations, how herbivores and their predators engaged in a continuous cycle of innovation and counter-innovation. This arms race, stretching across millions of years of Mesozoic time, transformed many herbivores into remarkable examples of evolutionary power, merging biology with survival instinct. Stay with us as we unravel these stories etched in stone and fossil. In the grand tapestry of life that unfolded over the Mesozoic era, the narrative of survival is often told as a story of teeth, claws, and predation. a relentless pursuit of the next meal by mighty carnivores. Yet, the story would be incomplete without the equally compelling saga of herbivorous dinosaurs and their evolutionary countermeasures. This chapter in Earth's ancient history is defined by an intricate arms race, a continuous sequence of adaptations and counter-adaptations between herbivores seeking to protect themselves and the predators striving to overcome those defenses. Understanding this evolutionary arms race sheds light on how these seemingly gentle giants evolved into some of the most formidable creatures in prehistoric ecosystems. An evolutionary arms race occurs when two or more species interact closely, typically predator and prey, leading to reciprocal adaptations. Predators evolve improved hunting techniques, sharper weapons, or greater speed, while prey species develop defensive strategies to avoid or deter attacks. These adaptations, in turn, influence each other in a continuous cycle over millions of years. Within the dinosaur world, this dynamic was especially pronounced due to the long coexistence of massive, diverse herbivorous clades and their equally formidable carnivorous counterparts. At the dawn of the dinosaur age, early herbivores were relatively small and lacked specialized defense mechanisms. Their primary mode of survival likely revolved around speed and hiding. However, as certain carnivores evolved in tandem, some growing larger, faster, and more efficient at hunting, the pressure on herbivores intensified. Evolution responded with an array of anatomical and behavioral defenses, producing dinosaurs that not only survived but thrived amid dangerous landscapes. One cornerstone of this arms race was the development of physical weaponry. Ceratopsians, a group that includes the iconic Triceratops, evolved elaborate cranial horn arrangements and expansive bony frills. These structures served multiple defensive roles. The horns could punch or gore attackers, while the frills shielded the neck from bites. Intriguingly, the evolution of these features also corresponded with social and sexual selection, further amplifying their development. Fossils show evidence of healed bite wounds near the frill and horn bases, indicating their active use in combat against predators or rivals. Similarly, stegosaurs sported formidable defensive tools in the form of a spiked tail called the thagomizer. Acting like a swinging club, these spikes could inflict severe injury on pursuing predators. Their plates, while debated, may have played roles in intimidation, thermoregulation, or species recognition, but their presence alongside the thagomizer speaks to an evolutionary investment in defense. The arms race here involved predators needing to devise ways to avoid the deadly tail or attack from less protected angles. Armored dinosaurs such as ankylosaurids and nodosaurids represent another pinnacle of defensive evolution. These living tanks carried heavy, thick osteoderms, bony plates embedded in their skin that provided an almost impenetrable shield against bites. The ankylosaurid's tail clubs evolved as offensive countermeasures, capable of delivering bone-crushing blows. These adaptations served as a direct response to predation pressure, forcing carnivores to either evolve stronger teeth or changing their hunting strategies to evade injury. Beyond weaponry and armor, evolutionary adaptations also included changes in behavior and sociality. Herding became a vital strategy, where numbers provided safety and complex group vigilance made successful attacks by predators more difficult. In addition to physical modifications, social behaviors could be seen as indirect defensive adaptations, shaped by the relentless demands of survival. Sheer size, particularly among sauropods, constituted another kind of defense. Towering over most predators, these giants relied on their massive bulk and long necks to access food sources beyond reach for others. Although their immense size limited their speed and agility, it often was enough to deter even the largest carnivores. Some sauropods also evolved whip-like tails, potentially used as deterrents or weapons, an unexpected but fascinating adaptation in the race between offense and defense. This arms race was not a linear progression, but a complex, branching tree of evolutionary experiments. Different herbivorous lineages evolved unique solutions based on their environments, predators, and lifestyles. For example, pachycephalosaurs developed reinforced, dome-shaped skulls hypothesized for headbutting. Whether for intraspecific combat or predator deflection remains debated, but underscores the diversity of adaptations forged through this arms race. Fossil records provide snapshots of these battles etched in bone. Puncture wounds, healed fractures, and scarred skulls reveal encounters where defenses and offenses clashed directly. Some herbivores show evidence of repeated combat, hinting at territorial disputes or mating battles, adding another layer of evolutionary pressure to adapt and arm themselves further. Importantly, the evolutionary arms race shaped not only survival, but also behavioral ecology. Defensive adaptations influenced predator hunting strategies, migration patterns of herds, and the broader ecological balance. This dynamic coevolution amplified the biological diversity and complexity within Mesozoic ecosystems, painting a vivid picture of life as a continuous contest, a dance of survival defined by challenge and response. Understanding this evolutionary arms race challenges the simplistic notion of herbivores as defenseless victims, revealing instead a world where they held their own with remarkable defensive arsenals. Their bodies became battlegrounds for natural selection, sculpted by millions of years of interaction with relentless predators. Through this lens, herbivorous dinosaurs transform from passive grazers into active, sometimes aggressive entities, equipped with the tools and tactics that made them dangerous and resilient. As we proceed deeper into the fascinating world of dinosaur defense, this evolutionary context provides the foundation for appreciating the unique adaptations featured in different groups. From bone armor to swinging tails, and from herding strategies to massive size, the arms race underscores the dynamic interplay that defined survival and dominance in prehistoric landscapes. The next chapters will bring these adaptations to life in vivid detail, focusing on specific dinosaurs and how their evolutionary responses manifested in both anatomy and behavior. The Mesozoic era, often dubbed the Age of Dinosaurs, spanned an immense stretch of time from about 252 million to 66 million years ago, encompassing the Triassic, Jurassic, and Cretaceous periods. Throughout these epochs, Earth's environments underwent profound shifts, geologically, climatically, and ecologically, that shaped the rise and evolution of the giant herbivores so integral to this era. Understanding the environmental theater in which these colossal plant eaters lived and thrived reveals the very stage upon which their evolutionary dramas, survival strategies, and dangerous adaptations played out. From the dawn of the Triassic period, the Earth's supercontinent Pangaea gradually began breaking apart, a process that dramatically influenced regional climates and ecosystems. The rearrangement of land masses altered ocean currents and atmospheric circulation patterns, leading to diverse habitats, from lush tropical forests to arid inland deserts. Such heterogeneity provided a wide variety of niches for dinosaurian herbivores to exploit, encouraging diversification in size, form, and behavior. One of the most significant environmental factors favoring the emergence and success of giant herbivorous dinosaurs was the proliferation of gymnosperm forests, dominated by conifers, cycads, and ginkgos, before the evolution of widespread flowering plants. These plants often grew into towering woodsy expanses, supplying enormous amounts of fibrous and sometimes tough vegetation. To feed on these abundant but challenging resources, some herbivores evolved exceptional size as an advantage, allowing them to reach high into the canopy, process large quantities of vegetation, and retain sufficient nutrients despite the low caloric density of some plants. The Jurassic period witnessed the rise of the iconic sauropods, giants like Brachiosaurus and Diplodocus. Their adaptations, long necks to access high foliage, massive gut chambers to ferment fibrous plant matter, reflect their intimate relationship with their ecosystem's flora. The evolution of such gigantism was not merely a biological curiosity, it was an ecological necessity. In these vast, forested landscapes, high competition for limited nutritious resources fueled an evolutionary premium on size and efficiency. Moving into the Cretaceous period, when angiosperms, flowering plants, began to diversify and dominate many habitats, herbivorous dinosaurs faced new challenges and opportunities. The nutritional profiles of plants altered, and with that, feeding strategies diversified. Hadrosaurs, known as duck-billed dinosaurs, evolved complex dental batteries adept at processing tough, flowering plants. Ceratopsians carved out their own niches with powerful jaws capable of shearing fibrous vegetation. This botanical evolution spurred an ecological cascade. As plants diversified, herbivores adapted in turn, reinforcing an ongoing dance of momentum between flora and fauna. Climate fluctuations throughout the Mesozoic further sculpted the landscapes and the lives of herbivorous dinosaurs. Generally warmer global temperatures and elevated atmospheric carbon dioxide levels supported lush vegetation growth, but also resulted in periods of drought and volcanic activity that challenged the resilience of ecosystems. Herbivores responded by developing not only physical defenses, but also behavioral adaptations, like migratory herding or habitat selection, to cope with environmental pressures. The presence of apex predators, including formidable theropods like Allosaurus and Tyrannosaurus, exerted relentless predation pressure that influenced herbivore distribution and social structures. Large herds of herbivores could often be found moving across floodplains and coastal lowlands, areas rich in vegetation but also risk-laden zones under predator scrutiny. This led to the evolution of defensive group behaviors and, consequently, the anatomical innovations we explore in subsequent sections. Water sources and terrain complexities further affected herbivore adaptations. Some species favored swampy, riverine environments where dense vegetation offered both food and shelter, while others inhabited rugged or upland areas. For instance, the ceratopsians, with their heavy skull armor, often lived in more open plains, where their defensive features were crucial for survival in exposed terrain. The enormous size of many herbivores also influenced their local ecosystems. Massive sauropods, by trampling vegetation and shaping forest structure, could create microhabitats utilized by other species, both plant and animal. Their fecal deposits enriched the soil with nutrients, promoting plant growth and contributing to carbon cycling. These environmental interactions suggest that herbivores were not mere passive participants, but active engineers of their landscapes. Moreover, the Mesozoic's environmental backdrop was far from static. Periodic events such as volcanic eruptions, sea level changes, and asteroid impacts introduced episodes of upheaval and change. These environmental stresses tested the adaptability of herbivores, favoring those with flexible feeding habits, behavioral plasticity, or robust physical defenses. Ultimately, the Mesozoic environment provided both the resources and those intense survival challenges that forged the herbivore's evolution. Ecological pressures, climate patterns, plant diversity, geographical changes, and predator-prey dynamics intertwined to create an evolutionary crucible. It was within this richly textured theater that giant herbivorous dinosaurs emerged, honed their defenses, and perfected strategies that blurred the lines between prey and formidable adversary. As we move forward to examine the fossil record and behavioral evidence, keep in mind this intricate environmental context. It sets the foundation for understanding not just what adaptations herbivores developed, but why these adaptations were necessary. The landscapes and climates of the Mesozoic were as much a part of their defense as horns and armor. Silent yet omnipresent forces guiding the destiny of these ancient giants. As we move deeper into understanding the complex realities of herbivorous dinosaurs, one challenge stands paramount. How can we, millions of years removed from their existence, interpret behavior, especially aggression and danger, from often fragmented fossil evidence? Paleontology, the science of studying ancient life through fossils, relies on an intricate array of clues. Bones marked by injuries, the anatomy of weaponry and defenses, the distribution and arrangement of fossils, and comparisons with living animals. Together, these clues provide a window into the lives of these ancient creatures, enabling us to infer how dangerous some herbivores truly were. Fossil evidence serves as the fundamental archive of prehistoric life, and paleontologists approach it with a meticulous eye. One of the key indicators of aggression or defensive use in herbivorous dinosaurs is the presence of injuries consistent with combat or predator interactions. Embedded bite marks on bones, areas of healed trauma, and fractures reveal past struggles. Remarkably, these wounds often show signs of healing, indicating that the dinosaur survived encounters that might have been truly life-threatening. For example, the skulls and frills of ceratopsians like Triceratops sometimes bear puncture wounds or scrapes from horn tips, clues suggestive of intraspecific combat, fights between members of the same species. These injuries are often concentrated around the protective frill and brow horns, precisely where one would expect blows from rivals seeking dominance, mates, or territory. This suggests not only aggressive defense against predators, but also social aggression, creating a complex picture of behavior. Similarly, stegosaurs often display healed injuries on their tail vertebrae, hinting at the use of their thagomizers in active defense. The tail spikes, when wielded with force, would leave marks if counterattacks occurred during battles with predators or rival stegosaurs. The presence of such injuries affirms that the tail was not merely a passive feature, but a dynamic weapon. Bone histology, the microscopic study of bone tissue, adds another layer to behavioral insights. By examining growth patterns and bone density, paleontologists can infer an individual's age, health, and sometimes stress events, including injuries. Rapid healing rates might correlate with aggressive lifestyles or frequent physical conflicts. Additionally, trackways and fossilized footprints provide a valuable behavioral snapshot, revealing the movement of dinosaur herds, speed, and interactions. Multiple parallel trackways of herbivores suggest social behavior such as herding, a strategy likely contributing to collective defense. Some track sites reveal traces of possible predator-prey chases, shedding light on how herbivores responded under threat, whether fleeing or standing their ground. The morphology of skeletal features provides another indispensable clue. Sharp, robust horns, thickened skull domes, formidable claws, and tail clubs all bear witness to an evolutionary history of defense and potential aggression. These structures are costly to develop and maintain, indicating strong selective pressure favoring their function in combat or deterrence. As a result, they are prime evidence of an aggressive or defensive behavioral repertoire. Comparative anatomy, drawing parallels between extinct dinosaurs and extant animals, allows scientists to hypothesize behavior based on similarities. Modern large herbivores like elephants, rhinoceroses, or bison use their tusks, horns, or sheer size in defense and social competition. While dinosaurs differ in many respects, Convergent evolutionary principles allow cautious inference that similar anatomical features served comparable functions in behavior. Moreover, the social organization implicated by fossil sites paints a picture of cooperative defense and perhaps aggression. Some bone beds reveal dense accumulations of individuals from the same species, including juveniles, adults, and elders, suggesting group living and parental care. These social structures elevate survival odds and complicate predator encounters, implying coordinated defense rather than solitary vulnerability. The rare preservation of soft tissues, though scarce, also enriches interpretations. Fossilized skin impressions indicate the presence of spines, scutes, and other defensive coverings, projecting an image of herbivores as armored warriors in their own right. Combined with skeletal weaponry, these coverings create a formidable line of defense. Intriguingly, fossils occasionally capture the aftermath of predator-prey confrontations in the form of embedded teeth or bone breakage patterns matching predator hunting styles. These encounter records reveal not only the dangers faced by herbivores, but also their resilience and capacity to inflict harm in return. Behavioral clues also emerge from examination of dinosaur reproductive biology. Evidence for nest defense, territoriality, and parental care imbues herbivores with protective instincts that could scale to aggressive behaviors. Defending vulnerable eggs and hatchlings would have necessitated readiness to confront threats, blurring the line between peaceful forager and fierce guardian. Piecing together fossil evidence with behavioral analogies, paleontologists construct increasingly sophisticated profiles of herbivorous dinosaur aggression and danger. Rather than passive megafauna, these animals emerge as active participants in complex ecosystems, combining anatomical weaponry, social strategies, and behavioral adaptability to navigate life's perils. As we prepare to examine particular groups in detail, from ankylosaurids with their bony clubs to the horned ceratopsians and beyond, this foundation equips us to appreciate the fossil-based stories that reveal these creatures as formidable giants. They defended themselves vigorously, competed fiercely, and sometimes even turned predator into prey. The stones and bones they left behind speak volumes about their struggles, survival, and the primal dance of aggression shaping the ancient world. Among the most iconic and visually striking of all herbivorous dinosaurs are the ankylosaurids, often affectionately dubbed the living tanks of the Mesozoic. These heavily armored quadrupeds present a masterclass in evolutionary defense, a testament to the perpetual struggle between predator and prey that unfolded over millions of years. In this chapter, we'll delve deeply into the fascinating world of ankylosaurids, their formidable bone armor, their lethal tail clubs, and the extraordinary ways these adaptations made them some of the most dangerous herbivores in prehistoric ecosystems. Ankylosaurids flourished primarily during the late Cretaceous period, roughly between 100 and 66 million years ago. Their wide distribution across ancient North America, Asia, and Europe underscores their evolutionary success and ecological significance. Unlike many other herbivorous dinosaurs, ankylosaurids embraced a slow-moving, heavily armored lifestyle that prioritized defense above speed or maneuverability. At first glance, an ankylosaurid's body appears almost impenetrable. The creature's back, flanks, and even parts of the limbs were sheathed in a mosaic of osteoderms, thick, bony plates embedded within the skin. These osteoderms varied in size and shape, from small nodules to large, flat plates, creating a natural shield that could absorb and deflect predator strikes. Scientists estimate that some ankylosaurids were covered by hundreds of these animals' own body armor, making them literal moving fortresses. The armor served multiple functions beyond mere passive protection. For example, the arrangement of osteoderms likely acted as a visual deterrent, signaling to predators that this was not an easy target. The rough, spiked texture could have discouraged predators from biting down, while the sheer bulk and weight of the armor made attacking costly. Additionally, some ankylosaurs had large spikes jutting from their bodies, forming likely barriers that made close contact dangerous. The crown jewel of ankylosaurid defensive anatomy lies in their tails, specifically, the evolution of the tail club. This structure consisted of a broad, rounded, bony mass at the distal end of the tail, supported by fused vertebrae that provided rigidity and power. The tail club functioned like a natural war hammer, swung with tremendous force to deliver crushing blows against aggressive predators or rival ankylosaurids. Biomechanical studies of tail club fossils reveal that ankylosaurids could swing their tails with surprising speed and strength. This weapon could break bones or cause severe injury to attackers, and even deter predators simply by demonstration. Remarkably, some specimens show healed injuries believed to be the result of tail strikes, attesting to the active defensive role these structures played in life. The evolution of the tail club was a significant leap from earlier armored dinosaurs, such as nodosaurids, which lacked such a weaponized tail. This difference reflects a fascinating divergence in defensive strategies within the ankylosaur family. Nodosaurids relied heavily on passive armor and shoulder spines, whereas ankylosaurids added an offensive weapon that could be wielded effectively. Feeding habits also complemented their defensive lifestyle. Ankylosaurids were low browsers, feeding on low-growing vegetation such as ferns, cycads, and other understory plants. Their wide, beaked mouths and leaf-shaped teeth were adapted for cropping, while their heavy bodies and armored exteriors meant they often fed in environments where maneuverability was less critical. Social behavior in ankylosaurids remains less certain due to fossil record limitations, but some evidence suggests these dinosaurs might have been solitary or lived in small groups. Given the effectiveness of their armor and weaponry, pack behavior may not have been essential for defense. Instead, their anatomy allowed individual ankylosaurids to confidently face dangers alone, turning potential vulnerability into strength. The predator-prey dynamics involving ankylosaurids present a dramatic glimpse into the dangers of the Mesozoic ecosystems. Large theropods like Tyrannosaurus rex undoubtedly posed threats, yet the sheer defensive apparatus of ankylosaurids meant that any attack carried substantial risk for the predator. Indeed, some fossils of T. rex display bite marks consistent with ankylosaurid encounters, with corresponding injuries found on ankylosaurid specimens, suggesting fierce battles between these prehistoric titans. Moreover, the ankylosaurid's armor and tail club likely had secondary uses, such as in intraspecific competition for mates or territory. Just as modern animals use their bodies for visible and physical displays of dominance, ankylosaurids may have swung their deadly tails not only against predators, but also rivals, broadcasting their fitness and strength. From a paleontological perspective, the discovery of well-preserved ankylosaurid fossils, sometimes with intact tail clubs and armor, has provided an extraordinary window into these armored warriors. Advances in imaging and biomechanical modeling have allowed scientists to reconstruct their movements and understand their role in prehistoric ecosystems with unprecedented depth. In summary, ankylosaurids exemplify how powerful the combination of defense and offense could be in herbivorous dinosaurs, challenging the notion of plant eaters as passive or defenseless. Their evolution as walking fortresses with bone-crushing clubs reshaped interactions within their ecological communities and secured their place as some of the most dangerous herbivores of the Cretaceous. In the next chapter, we will explore another remarkable group known for their impressive weaponry and defensive tactics, the ceratopsians, renowned for their iconic 3 horns and protective frills. Understanding these creatures will further illuminate the ingenious ways herbivorous dinosaurs transformed vulnerabilities into formidable defenses, a theme at the heart of their ancient survival. Triceratops stands among the most recognizable and emblematic herbivorous dinosaurs, known worldwide for its striking appearance characterized by 3 imposing facial horns and a massive bony frill. Living during the late Cretaceous period, approximately 68 to 66 million years ago, Triceratops epitomizes the evolutionary solutions herbivores developed to confront the myriad dangers lurking in their prehistoric world. In this chapter, we unravel the enigma of Triceratops, examining the form and function of its iconic horns and frill, its defensive tactics, and the ongoing scientific debates about its lifestyle and behavior that continue to captivate paleontologists and enthusiasts alike. Triceratops belonged to the Ceratopsidae family, a group renowned for horned faces and ornate frills. Yet this genus was exceptional in several ways. With an estimated length of up to 9 meters, around 30 feet, and weighing between 6 to 12 tons, it was a colossal presence, dwarfing many contemporaries. Its name, meaning three-horned face, aptly highlights its main weapons: 2 large brow horns projecting over the eyes and a shorter nasal horn on its snout. These horns could measure over 1 meter in length, brute structures seemingly designed not just for show, but for active defense. The function of these horns has been extensively studied and debated. Early theories painted Triceratops primarily as a weed-eater, using the horns largely as intimidation or social display features. However, an accumulation of evidence over recent decades has reshaped this view, revealing the horns were formidable weapons against both predators and competitors. The horns atop the eyes likely served multiple functions. They could be wielded to gore and fend off attacks from apex carnivores like Tyrannosaurus rex, which shared the same territories. Fossil evidence, including T-Rex skulls with puncture wounds matching Triceratops' horn dimensions and Triceratops bones bearing healed bite marks, supports this notion of intense predator-prey dynamics. The nasal horn, although smaller, possibly played a role in close-quarter defense or in combat with rivals. Complementing the horns was the distinctive frill, a wide, thickened plate of bone extending from the back of the skull. Initially thought to be purely a protective shield guarding the neck, modern research suggests the frill's role could have been multifaceted. Its robust construction would have provided a physical barrier against predator bites aimed at vulnerable neck areas. Additionally, its large surface area may have been a canvas for species recognition, sexual display, or thermoregulation. Perhaps one of the most fascinating windows into Triceratops' behavior comes from fossilized injuries concentrated on the frill and horns. Researchers have identified lesions and punctures in the frill consistent with horn strikes from other Triceratops, indicating intraspecific combat. These battles could have been related to territorial disputes, competition for mates, or establishing dominance hierarchies. Behavior patterns remarkably similar to modern horned animals, such as bison or antelope. This evidence highlights a complex social life behind the seemingly placid herbivore, where aggressive encounters between individuals demanded not only impressive offensive tools, but also strategies to minimize lethal outcomes, signaling that the horns and frill were as much about ritualized combat and communication as raw violence. In terms of locomotion and feeding, Triceratops was a sturdy quadruped with robust limbs capable of supporting its heavy armor and massive skull. Its jaws contained a shearing dental battery designed to slice through tough, fibrous plant material, such as cycads, palms, and conifers common in late Cretaceous environments. This feeding adaptation allowed it to exploit abundant but challenging vegetation, providing the energy needed to sustain its large body and energetically costly defensive structures. The environment Triceratops inhabited, primarily the river floodplains and coastal plains of what is now North America, was home not only to prolific carnivores, but also to rich, diverse herbivore communities. Competition for resources may have reinforced territorial behavior and the need for effective individual defense mechanisms. Scientific debates continue regarding Triceratops's lifestyle. Some researchers argue it lived in herds, using collective defense against predators, while others suggest a more solitary or small group existence, relying mainly on its physical defenses and aggressive displays. Emerging technology, such as biomechanical modeling and CT imaging of fossilized skulls, is providing fresh insights into horn strength, frill structure, and bite forces, enhancing our understanding of how this dinosaur lived and fought. Triceratops's enigma, then, lies in this blend of power, defense, and possible social complexity. Its massive horns and frill were not mere ornaments, but lethal tools and protective armor, forged by evolutionary pressures where danger was a constant companion. It was a creature capable of formidable defensive offense, transforming it from prey to a respected rival in the dangerous arenas of the Cretaceous. Looking forward, as we explore other herbivorous dinosaurs with unique adaptations, such as stegosaurs with their devastating tail spikes, we continue to uncover the diverse and surprising ways in which plant eaters defended themselves. Triceratops stands as a pinnacle of this evolutionary journey, a living enigma whose legacy endures as a symbol of the power and resilience of herbivorous dinosaurs. Stegosaurs represent one of the most fascinating and visually distinct groups of herbivorous dinosaurs, immediately recognizable by their iconic backplates and formidable, spiked tail weaponry known as the thagomizer. From the Jurassic period, roughly 155 to 150 million years ago, stegosaurs thrived amidst the primeval landscapes, embodying an evolutionary masterpiece in defense strategies. This chapter explores the anatomy, functionality, and behavioral implications of the stegosaurian defensive arsenal, examining how these creatures wielded their unique adaptations to survive the perilous world of Mesozoic ecosystems. The stegosaurian silhouette is instantly memorable, a robust, squat body balanced upon powerful hind limbs and shorter forelimbs, with a double row of large, often triangular plates rising from their backs. The plates, varying in shape, size, and arrangement across species such as Stegosaurus, Kentrosaurus, and Tuojiangosaurus, have sparked rich debates among paleontologists regarding their primary functions. While these structures may have played roles in species recognition and thermoregulation, their role as defensive features cannot be overlooked. The real star of stegosaur defense, however, lies in the tail region. At the end of the tail, most stegosaur species possessed a set of long, sharp spikes, a weapon system scientifically dubbed the thagomizer, borrowing its name from a humorous 1980s comic strip, but now widely embraced in paleontological discourse. Typically, this weapon comprised 4 to 6 robust spikes, capable of delivering powerful swinging blows to any predator daring to approach from behind. Biomechanical reconstructions indicate that stegosaurs could swing their tails with significant force and precision. The muscular hindquarters and vertebral articulations provided both flexibility and strength necessary to make the thagomizer a lethal defense mechanism. This swinging tail could puncture flesh, break bones, and deter even large theropods like Allosaurus or Ceratosaurus. Fossil evidence, including puncture wounds on predator bones matching thagomizer spike shapes, corroborates the tail's active role in defense. The plates along the back may have served as an intimidation device. When threatened, stegosaurs might have lifted their bodies or arched their backs to present a more imposing profile. Such a display, coupled with the visible menace of their tail spikes, would have sent a clear warning to predators. Attacking this armored herbivore was a dangerous proposition. Some models also suggest the plates served in thermoregulation, helping the animal dissipate heat or absorb warmth, an essential function in their often warm and seasonal habitats. The evolution of the thagomizer represents a remarkable example of evolutionary innovation in herbivorous dinosaurs. Early relatives of stegosaurs, like Huayangosaurus, show rudimentary spikes, indicating a gradual refinement of this weapon over millions of years. This evolutionary pressure stemmed from the presence of aggressive predators in their ecosystems, necessitating a tail more than just a balancing appendage. It had to become a powerful weapon. Behavioral implications of the stegosaur defensive system extend beyond predator interactions. The thagomizer might have been used in intraspecific conflicts, such as fights over mates or hierarchical dominance. Just as modern animals utilize horns or antlers in ritualized combat, stegosaurs could have employed their tails in displays of strength or territorial contests. The robust nature of the tail spikes supports the idea that repeated use in combat was not only possible but likely. Stegosaurs' feeding strategies also complemented their defensive anatomy. With relatively small heads and peg-like teeth, they were low browsers, nibbling on ferns, cycads, and other understory vegetation. Their less nimble bodies suggested limited escape capability, further emphasizing the importance of their defensive adaptations. When threatened, a stegosaur's best strategy was not flight, but turning its lethal tail against the aggressor. Fossils provide compelling snapshots of the stegosaur world, with some specimens bearing healed injuries that indicate survival of violent encounters. The matching injuries on predator fossils from the same strata add a dynamic dimension to predator-prey relationships, where both attacker and defender bore the scars of their evolutionary arms race. In summary, stegosaurs uniquely exemplify the combination of defense through physical modification and strategic behavior. The vivid outline of their plated back and swinging, spiked tail is not just a static image, but a story of adaptation, survival, and the primal tension of life during the Jurassic. As we continue our survey of herbivore defenses, stegosaurs remind us that danger and protection are intertwined in the evolutionary saga, a dance of death and survival played out through time on ancient landscapes. In the following chapter, we will encounter the diverse world of horned ceratopsians, exploring their powerful frills and horns and the vibrant social dynamics that made them some of the most dangerous herbivorous dinosaurs of the Cretaceous. The spectacular diversity of horned dinosaurs in the late Cretaceous is a testament to evolutionary creativity, and among them, the ceratopsians stand out as particularly fascinating. Within this group, two major subfamilies emerged, the chasmosaurins and the centrosaurins. Known collectively as the horned dinosaurs, these two clans embody a remarkable range of defensive adaptations, aggressive displays, and social behaviors. Their bone-crushing horns, massive frills, and fierce reputations have earned them a well-deserved place as some of the most dangerous herbivores that roamed the Earth prior to the end of the age of dinosaurs. Chasmosaurines, typified by dinosaurs such as Triceratops and Pentaceratops, possessed long brow horns that could extend over a meter in length and a comparatively large, elongated frill. In contrast, centrosaurins like Styracosaurus and Centrosaurus exhibited shorter brow horns, but compensated with extravagant nasal horns and frills decked with an array of spikes and hooks. This divergence in morphology reflects differing ecological roles and behavior modes, yet both groups were fully equipped for formidable defense and intra-species competition. The horn arrangements alone evoke images of prehistoric battles, where these massive herbivores locked horns and exchanged blows, not only to defend against ferocious carnivores, but also to assert dominance within their own kind. Paleontological evidence reveals numerous skulls marred by horn-inflicted injuries, both healed and fatal, attesting to frequent clashes that likely served functions from securing mates to defending territories. Chesmosaurines, with their long, sharp brow horns and massive size, were perhaps the most physically imposing of the horned dinosaurs. Triceratops exemplifies this style of defense. Two elongated horns above the eyes capable of powerful thrusts, combined with a massive domed skull and a broad frill offering protection to the neck and shoulders. This design provided both offensive and defensive capabilities, allowing them to stand their ground against apex predators like Tyrannosaurus rex. The frills, especially in chasmosaurines, were often less ornamented than those of centrosaurines, but bigger and sturdier, capable of shielding vital areas. These frills likely evolved under a complex mix of selective pressures, including protection from bites and social signaling. Some studies suggest the frills bore vital blood vessels, acting as thermoregulatory devices, while others emphasize their role in visual displays, flashing colors or patterns possibly used to communicate status or attract mates. Centrosaurines, on the other hand, embraced an altogether different evolutionary path. Their shorter brow horns were complemented by oversized nasal horns or bosses and elaborately decorated frills adorned with spikes and hooks that could intimidate rivals or predators alike. Styracosaurus's formidable nasal horn, reaching over 60 centimeters in length, combined with a halo of frill spikes, created an intimidating visage capable of matching any predator's ferocity. This ornamental complexity suggests centrosaurines placed a higher emphasis on display and social behavior, potentially living in larger herds where visual signals were critical for cohesion and hierarchy. Yet, their spiky adaptations were far from mere decoration. The dense arrays of frill spikes could inflict painful injuries upon attackers or rival dinosaurs, acting as passive defense that complicated any attempt at a neck bite. Behaviorally, both groups are thought to have engaged in ritualized combat, using their horns and frill ornamentations to challenge rivals without immediately resorting to lethal violence, mirroring the behavior of modern horned mammals, where escalation is often measured and symbolic. However, the heavy cranial weaponry was always ready to be wielded if required. Fossil evidence includes puncture wounds, healed fractures, and embedded bone chips that confirm violent encounters. Socially, many ceratopsians lived in herds, as indicated by multiple bone beds containing dozens to hundreds of individuals, ranging from juveniles to fully mature adults. Such social living demanded coordinated defense strategies and facilitated the transmission of learned protective behaviors. Herding also magnified the danger these herbivores posed to predators, as multiple horned dinosaurs could present a formidable wall of spiked heads. The diversity between chasmosaurines and centrosaurines is a vivid reminder of how evolutionary pressures can craft multiple solutions to survival challenges. While sharing fundamental traits such as robust horns and protective frills, each subfamily carved out distinct ecological and behavioral niches, resulting in a spectrum of defensive tactics. Collectively, the horned dinosaurs demonstrate how herbivores were neither powerless nor passive. Instead, their dramatic headgear and social behaviors turned them into living fortresses and aggressive combatants on the ancient plains. Their legacy echoes not only in the fossil record, but also in modern understandings of how vulnerability can evolve into strength. As we proceed to explore other fascinating groups, such as the enigmatic dome-headed pachycephalosaurs, we will continue to unravel the spectacular diversity and surprising strategies that defined the most dangerous herbivorous dinosaurs. Among the most enigmatic and intriguing of the herbivorous dinosaurs are the pachycephalosaurs, distinguished by their distinctive, thick, dome-shaped skulls and, in many species, an array of formidable spikes and knobs adorning their heads and necks. Often referred to as the dome-headed dinosaurs, pachycephalosaurs thrived during the late Cretaceous period, approximately 85 to 66 million years ago, particularly across what is now North America and Asia. This group's unique cranial morphology has sparked scientific debate and fascination regarding its purpose, most notably whether these creatures used their stunning skulls as weapons in combat, a feature that positions them among the more dangerous herbivores of their time. At the heart of the pachycephalosaur mystery lies the thickened dome atop their skulls, composed of dense, solid bone, sometimes over 25 centimeters thick. This incredible structure was not mere ornamentation. It was biologically remarkable, exhibiting strong architectural reinforcement suitable for withstanding significant impacts. The surrounding skull edges were often ornamented with spikes and nodules, providing additional defense mechanisms resembling a spiked shield. These cranial armaments served various functions, from species recognition and sexual display to, most intriguingly, active combat. The most widely supported hypothesis regarding pachycephalosaur behavior is that these dinosaurs engaged in head-butting or flank-butting contests. Similar to some modern animals, such as bighorn sheep or musk oxen, males may have rammed their domes into one another in fights for territory or mating rights. The dome's construction, with its thick bone and shock-absorbing internal structure, suggests it was well adapted to absorb repeated impacts without incurring fatal damage. Supporting this combat hypothesis, fossil evidence has uncovered signs of healed cranial lesions and puncture wounds on some pachycephalosaur skulls consistent with blunt force trauma. These injuries indicate not only the use of the dome in aggressive encounters, but also the ability of these animals to survive such clashes, suggesting that physical combat was an integral part of their behavior rather than relatively rare accidents. Moreover, the spiked ornamentation around the dome and along the neck region likely served to protect vulnerable areas during combat, discouraging opponents from striking them and protecting the skull base and cervical vertebrae. The spines and knobs could have also played a role in intimidating rivals or predators, adding an extra layer of defense beyond the dome itself. Debate continues regarding the exact mechanics of pachycephalosaur combat. Some scientists propose direct, head-on ramming, while others suggest a more angled flank-butting style, reducing the risk of fatal injuries. The latter hypothesis is bolstered by biomechanical modeling, which shows that the shape and placement of the dome could absorb impacts delivered at slight angles, while the robust neck musculature provided the necessary force for these strikes. Such tactics would combine both offense and defense, aggressively asserting dominance, but with techniques refined to avoid deadly harm. Beyond combat, pachycephalosaurs were herbivores with adaptations suitable for browsing low-lying vegetation or selectively feeding on specific plants. Their relatively small teeth and jaws indicate a diet that did not require heavy chewing, possibly including leaves, fruits, and seeds. Their overall body structure, a bipedal stance with a somewhat stiff tail, would have given them agility and flexibility, useful both in foraging and in evasive maneuvers when confronted by predators. Pachycephalosaur fossils have been found in various environments, including floodplains and forested areas, suggesting adaptability to different habitats, potentially influencing their social structures. While direct evidence of herd behavior is limited, the complexity of their cranial ornamentation hints at the importance of visual displays within their social interactions, whether in courtship or conflict. The enigmatic nature of pachycephalosaurs expands our understanding of herbivore diversity and danger in the dinosaur world. Their thick domes and spiked shields were not merely for show. They were involved in behaviors that required significant strength, resilience, and aggression. These adaptations underscore a lifestyle in which combat and defense played vital roles, elevating these dome-headed dinosaurs well beyond the stereotype of docile plant eaters. As we continue to explore the myriad ways herbivorous dinosaurs protected themselves from predators and rivals, the pachycephalosaurs invite us to imagine a world where brains and brawn combined, where spectacular headgear was wielded not only as a symbol, but as a potent weapon. The mysteries of their dome-headed combat remain a captivating testament to the complex ecology and behavior that defined the age of dinosaurs. Next, we will delve into the survival tactics of hadrosaurs, the duckbills. Though lacking the obvious weaponry of pachycephalosaurs and ceratopsians, these dinosaurs employed size, speed, and social defense strategies that made them dangerous in their own right. In the dynamic world of the late Cretaceous, hadrosaurs, commonly known as duck-billed dinosaurs, represent one of the most successful and diverse groups of herbivorous dinosaurs. Their widespread presence across what is now North America, Asia, and Europe, combined with their impressive fossil record, offers a captivating story of adaptation and survival in a world marked by threats from formidable predators. Though lacking the obvious weaponry of the horned ceratopsians or the armored ankylosaurids, hadrosaurs evolved a suite of survival tactics centered around impressive size, swift movement, and sophisticated social defense strategies. This chapter delves into the myriad ways these giants thrived against the backdrop of Mesozoic danger. Hadrosaurs ranged in size from modestly sized species a few meters long to behemoths stretching up to 15 meters or more, tipping the scales at several tons. This considerable size served as one of their primary defenses. Large size inherently limits the number of predators capable of taking down an individual, thereby reducing vulnerability. The sheer bulk of adult hadrosaurs likely dissuaded attacks from many theropod predators, who generally preferred easier prey. Yet, size alone would not suffice without the complement of speed and agility, particularly for juveniles and smaller species within the group. Adaptations in limb structure highlight their capacity for surprisingly swift locomotion. Hadrosaurs had powerful hind limbs, well-developed musculature, and long strides, allowing for efficient bipedal and quadrupedal movement. This dual ability to move on 2 or 4 legs gave them remarkable versatility. They could sprint on 2 legs when fleeing danger and shift to 4 legs for stability during feeding or long-distance travel. This combination facilitated effective escape responses against pursuing predators, enabling rapid bursts of speed and agile maneuvering through diverse terrains. Beyond physical attributes, evidence strongly supports sophisticated social behavior among hadrosaurs, which served as a critical element in their defense. Fossil sites with massive bone beds containing hundreds or thousands of individuals of varying ages point toward herd living. The power of numbers provided not just safety, but a complex social structure with potential for coordinated defense. Living in large herds would make individual predation more difficult. Predators faced with a mass of alert, fast-moving animals risked injury and reduced success rates. Moreover, herding allowed for sentinel behaviors, individuals acting as lookouts, alerting the group to approaching dangers through vocalizations or visual signals. Hadrosaurs are believed to have possessed complex vocal organs and resonating chambers in their skulls, enabling them to produce a variety of sounds. These vocalizations likely played roles in communication during foraging, mating, social bonding, and crucially, alarm calls to warn of predatory threats. Hadrosaurs' dental and jaw adaptations are also integral to their survival story. Their complex dental batteries contained hundreds of teeth arranged in tightly packed rows, which they constantly replaced, allowing them to process tough, fibrous vegetation efficiently. This enabled long foraging periods efficiently, reducing exposure to predators while feeding compared to herbivores with less efficient chewing apparatuses. The combination of size, speed, and sociality paints a picture of hadrosaurs as herbivores who relied on keen awareness, group coordination, and swift movement to survive. They could evade predators not through brute force, but by outmaneuvering them and leveraging herd vigilance. Juveniles and weaker individuals likely found protection within the herd's center, while adults formed a mobile shield on the periphery. Interestingly, hadrosaur fossils occasionally show signs of healed injuries and bite marks, hinting that despite their survival strategies, conflict with predators was a frequent reality. Their success reflects not only biological and anatomical adaptations, but behavioral resilience, the ability to detect, respond to, and survive threats collectively. In summary, hadrosaurs epitomize a different path among the most dangerous herbivores. Rather than relying on physical weapons like horns or armor, they combined large size, nimble speed, and social cooperation. These factors made them formidable in their own right, capable of withstanding the predatory pressures of the Cretaceous with remarkable effectiveness. As we transition to examine the might of the enormous sauropods in the next chapter, bear in mind the diversity of herbivorous strategies shaped by evolution. From armor and weaponry to speed and social defense, giant plant eaters mastered an array of tactics to survive in ancient ecosystems teeming with danger. The colossal sauropods, towering giants with long necks and whip-like tails, are emblematic of the Mesozoic world, conjuring images of creatures so immense they seemed beyond the reach of any predator. Indeed, their sheer size is often considered the ultimate defense, a natural barrier against attack that few could overcome. But was their massive bulk truly enough to make these herbivores untouchable? In this chapter, we explore the evolutionary advantages and vulnerabilities of sauropod gigantism, examining how their unprecedented size shaped their survival strategies and their interactions within ancient ecosystems. Sauropods, including the likes of Argentinosaurus, Brachiosaurus, and Diplodocus, were among the largest animals to ever walk the Earth. Lengths often exceeded 20 meters, with some species surpassing 30 meters, and weights reaching upwards of 50 metric tons. This scale was not achieved overnight. Over millions of years, sauropods evolved gigantism as a remarkable adaptation with broad ecological implications. The advantages of immense size for defense are compelling. Large sauropods presented monstrous obstacles to predators, too big to be easily tackled or subdued. Predators generally prefer prey that can be captured and killed with reasonable effort and minimal risk. The energy investment and physical danger involved in attacking a sauropod, with its overwhelming mass, meant many carnivores likely avoided mature adults whenever possible. This size refuge functioned as a passive but highly effective defense. Moreover, giant sauropods benefited from their long necks, which allowed them to graze from vast vertical ranges without moving their heavy bodies excessively. This capability reduced exposure to predators, as they could feed in safer locations while accessing a wide array of vegetation. Their sheer presence might have also served as a deterrent. A massive adult represented an indomitable force within their environment. However, size did not render sauropods completely invulnerable. Juvenile and subadult individuals were far more exposed, susceptible to predation by large theropods such as the Allosaurus in the Jurassic or Mapusaurus in the Cretaceous. Fossil evidence from bone beds indicates that predators hunted these younger sauropods opportunistically, targeting the more vulnerable population segments. Even for adults, attacking a sauropod was not impossible, but the risks were substantial. Sauropods' tails, especially in species like Diplodocus and Shunosaurus, evolved into whip-like structures that could be wielded as powerful defensive weapons. These tails could deliver high-velocity blows capable of injuring or deterring attackers. The musculoskeletal configuration at the base of the tail suggests they had strong musculature, enabling swift lateral movements, and some researchers suggest the tail's snapping action could have produced a loud sonic boom akin to a cracking whip, potentially startling predators. Mobility was another factor influencing sauropod defense. Despite their size, sauropods were capable of moderate speeds, sufficient to move away from threats, especially across open grounds. Their massive legs supported their weight with robust bones and joints adapted for sustaining long-distance locomotion, although they could not sprint as fast as smaller, more agile predators. Social behaviors may have further augmented their survival. Evidence from trackways and fossil sites suggests that many sauropods traveled in groups, perhaps family units or mixed-age herds. Collectively, such groups presented a formidable obstacle, reducing individual predation risk. Group living also facilitated synchronized movements, defensive positioning, and perhaps communal vigilance against predators, a behavioral advantage complementing their physical bulk. Yet, the enormous size of sauropods brought challenges. Their metabolic needs required them to consume vast quantities of vegetation daily, necessitating efficient foraging strategies. In times of resource scarcity, their size became a liability, restricting movement speed and dietary flexibility. Additionally, growing from vulnerable hatchlings to massive adults demanded extended periods during which younger sauropods were particularly at risk. Fossil evidence hints at the intense predator-prey dynamics involving sauropods. Tooth marks found on sauropod bones exhibit that bites from giant theropods were sometimes powerful enough to cause bone fractures, indicating determined attacks. Scars on sauropod vertebrae suggest they survived such encounters, reflecting their resilience. The interplay between predator persistence and sauropod defense exemplifies nature's ongoing arms race. In conclusion, the massive might of sauropods provided one of the most effective natural defenses in the dinosaur age. Their colossal size created a form of untouchability, deterring most predators from attempting attacks on mature individuals. However, this defense was not absolute. Juveniles, sickly individuals, and perhaps isolated adults remained vulnerable. Their tails, group behaviors, and sheer presence combined to create a formidable survival package. As we delve further into the specific adaptations of these giants, including the whip-like tails and defensive warfare encoded within their anatomy, it becomes clear that size was merely one dimension of sauropod defense, a remarkable but complex evolutionary strategy molded by the perilous world they inhabited. Next, we will examine the fascinating case of Shunosaurus and other sauropods equipped with whip-like tails, revealing how these often overlooked weapons transformed herbivore defense. Among the vast array of sauropods that roamed the Mesozoic landscapes, a particularly fascinating subset evolved an unexpected and potent defensive adaptation: whip-like tails armed with bony clubs or spikes. Shunosaurus, a lesser-known but remarkable Jurassic sauropod from what is now China, stands as a prime example of these specialized tail weapons. Organic maces that transformed their massive but otherwise defenseless bodies into formidable instruments of survival. In this chapter, we explore the anatomy, function, and evolutionary significance of Shunosaurus and other whip-tailed sauropods, revealing how these massive giants wielded their tails as weapons of mass destruction in a perilous world. Shunosaurus lived during the Middle Jurassic period, approximately 165 million years ago, and measured around 9 to 11 meters in length. A medium-sized sauropod by later standards, but still impressive in its time. What sets Shunosaurus apart is the distinctive presence of a tail club formed by fused vertebrae and bony osteoderms, resulting in a bulbous, spiked mass at the tip of its long, flexible tail. This morphology suggests a dual role for the tail: a dynamic tool for balance and a potent defensive weapon capable of delivering powerful blows. The biomechanics involved in wielding such a tail indicate considerable muscular strength and flexibility. Shunosaurus could presumably swing its tail rapidly, much like a modern-day animal wielding a club, striking approaching predators or rivals with tremendous force. Paleontologists speculate that such an impact could cause severe injury or even be fatal, serving as a potent deterrent to predatory theropods like Sinraptor that shared its environment. Interestingly, Shunosaurus is not alone in developing such tail weaponry. Other sauropods with whip-like tails, such as Mamenchisaurus and some diplodocids, exhibit elongated, flexible tails with vertebrae that taper like a lash. While many diplodocids lacked the bony club seen in Shunosaurus, their tails nonetheless could generate significant speed and momentum, making a formidable sonic whip-like weapon capable of inflicting lacerations or stunning blows. Fossil evidence reinforces this interpretation. Trackways, tail vertebrae morphology, and rare cases of fine-tuned osteological architecture demonstrate that selection pressures favored not only size and bulk, but also active defensive tools. In contexts where sheer size could not guarantee protection, especially against agile predators capable of attacking vulnerable flanks or tails, these tail weapons offered sauropods an essential advantage. Tail weaponry in sauropods represents an evolutionary innovation complementary to their colossal size, providing a mobile defense capable of surprising speed and devastating impact. It showcases that even among the largest creatures, natural selection favored adaptations that actively deterred and repelled threats, rather than relying solely on mass or passive protection. Beyond pure defense, these whip-like tails may also have played a role in intraspecific interactions, dominance contests, mating displays, or territorial disputes. Using the tail as a weapon in ritualized combat would have shaped social behaviors within these sauropod populations, enriching the complexity of their lives and further underscoring the multifunctionality of this unique adaptation. The evolution of whip-like tails in sauropods, such as Shunosaurus, reflects a broader theme in herbivore defense: that survival in a world ruled by carnivores demanded not just passive traits, but active, often unexpected weapons. These massive dinosaurs, often imagined as benign, gentle giants, wielded their tails as mass destruction tools, bridging biology with brutal pragmatism. As we continue, the story of therizinosaurs beckons, a group known for colossal elongated claws far exceeding the length of a human arm. We will ask, were these creatures gentle giants or savage defenders wielding natural weapons of terror? The diversity of herbivorous dinosaurs will continue to astonish and enlighten us with each turn of paleontological discovery. Therizinosaurs stand among the most extraordinary and enigmatic of herbivorous dinosaurs, intriguing scientists and enthusiasts alike with their astonishing appearance, marked by colossal scythe-like claws longer than a human arm, elongated necks, and pot-bellied torsos. Living during the late Cretaceous period, approximately 100 to 70 million years ago, mainly in Asia and North America, these dinosaurs challenge conventional expectations of herbivore morphology and behavior. Were these giants gentle browsers peacefully gathering vegetation, or did they wield their immense claws as savage weapons, defending themselves fiercely from predators or rival conspecifics? This chapter explores the anatomy, behavior, and defensive capabilities of therizinosaurs, uncovering the intriguing duality of their nature. Therizinosaurs belong to the theropod group, ironically a lineage mostly composed of carnivorous dinosaurs, yet they evolved into herbivores displaying quite unique adaptations. Their most striking feature, the enormous manual claws, could reach lengths of up to a meter, making them some of the longest claws known in the dinosaur world. The function of these claws has been the subject of extensive debate. Early hypotheses considered them instruments of predation or prey capture, consistent with their theropod ancestry. However, subsequent research and anatomical studies suggest a shift towards herbivory, with claws adapted for pulling down branches, stripping foliage, or digging for roots. Yet, the potential for these claws to serve as formidable defensive weapons cannot be overlooked. The claws' size, curvature, and robust bone structure imply they could deliver powerful and potentially lethal slashes if used against predators or competitors. The musculature inferred from attachment sites suggests significant strength and dexterity, enabling controlled and forceful movements. In defense scenarios, a therizinosaur could arguably lash out with incredible speed, deterring attacks from large carnivores such as tyrannosaurids or dromaeosaurs. Further supporting their defensive potential, therizinosaurs possessed a large body size. Some species like Therizinosaurus reached lengths of up to 12 meters and likely weighed multiple tons. This mass alone would have made any confrontation risky for a predator. Their bulky torsos housed extensive digestive systems suited to processing large volumes of plant matter, but simultaneously served as a physical barrier. Behaviorally, therizinosaurs probably combined passive defense strategies such as intimidation display, vocalizations, and posturing, with active defense using their claws. Fossil evidence hints at healed fractures and injuries compatible with intraspecies combat or predator encounters, pointing to a lifestyle where confrontation was not uncommon. Their slow, lumbering gait may not have permitted rapid escape, reinforcing the expression that their claws were key survival tools. The necks of therizinosaurs were long and flexible, permitting them to access a broad range of vegetation while standing relatively in place. This adaptation was energy efficient, but also allowed them to keep a watchful eye for threats, promoting timely defensive responses. Spinal features indicate strong neck muscles, which could have been used to swing the massive forelimbs effectively. Interestingly, their feet and limbs were also adapted for stability rather than speed. Broad, weight-bearing structures suitable for supporting heavy bodies rather than rapid pursuit or evasive maneuvers. This adds to the notion that their survival hinged more on physical defenses and intimidation than flight. In many ways, therizinosaurs blur the line between gentle giants and fierce defenders. While primarily plant eaters relying on size and specialized feeding strategies, their anatomical features allow us to envision a creature that could fiercely defend its life and space with devastating armaments. They exemplify the evolutionary plasticity of dinosaurs, how traits inherited from carnivorous ancestors could be repurposed and amplified to fit a new ecological role. As paleontologists continue to uncover fossils and employ new technologies like biomechanical modeling and digital reconstructions, our understanding of therizinosaurs' lifestyle grows richer and more nuanced. These dinosaurs stand as a vivid reminder that danger and defense in herbivorous dinosaurs were not simply about horns and armor, but also about the subtle and surprising ways evolution crafts survival. Following this exploration into the monstrous claws of therizinosaurs, we will next examine the giant iguanodonts and their iconic thumb spikes, a different yet equally fascinating defensive adaptation that made these herbivores noteworthy warriors in their ancient worlds. Giant iguanodonts, towering behemoths of the early to late Cretaceous period, carve out a remarkable niche in the evolutionary narrative of herbivorous dinosaurs, particularly owing to one of their most distinctive features: the thumb spike. These formidable spikes, sometimes exceeding the length of a human hand, serve as a vivid testament to how herbivores evolved defensive and offensive adaptations that transcended mere passive protection. In this chapter, we delve deep into the anatomy, potential uses, and combat scenarios in which giant iguanodonts wielded their thumb spikes, from ancient predator confrontations to social battles within their own ranks. At first glance, the iguanodonts, exemplified by genera such as Iguanodon and Mantellisaurus, bear the hallmarks of powerful, agile herbivores. Their robust, elongated bodies, large limb muscles, and versatile locomotion, capable of switching between bipedal and quadrupedal movement, allowed them to cover ground efficiently while foraging across diverse Cretaceous environments. Yet, it is the falcon-like thumb spike that commands attention. A conical, laterally compressed bone projecting from the hand at the base of the thumb. Anatomical studies reveal that this thumb spike was highly adapted as a weapon. Strong musculature and tendons attached to the thumb allowed for controlled, forceful movements. This modular weapon was capable of slicing and stabbing, and it was likely wielded with precision. Fossil specimens reveal wear patterns on the spikes consistent with use, possibly for defense against predators or offensive actions during intra-specific conflicts. Ecologically, giant iguanodonts inhabited landscapes shared with formidable carnivores, including allosaurids and large theropods such as Neovenator. The presence of the thumb spike may have significantly bolstered their ability to deter or incapacitate would-be attackers before lethal bites or claw strikes could be delivered. Unlike heavy armor or horns, the thumb spike offered a swift and versatile form of active defense. In addition to defense from predators, the thumb spike likely played a role in social interactions, including dominance displays and territorial battles. Recent paleontological evidence suggests that iguanodonts engaged in ritualized combat, partly indicated by healed injuries on bones and inferred behavior patterns analogous to modern horned mammals. The thumb spike could have been used to jab or slash rivals in contests for mates or social rank, helping to establish hierarchies without fatal outcomes. Biomechanical modeling has provided nuanced insights into how the thumb spike was used. The range of motion and muscular attachments suggest the iguanodont could swing or jab its thumb rapidly sideways or downwards, targeting sensitive regions of aggressors, such as limbs or softer tissue areas. The ability to switch between locomotion modes, combined with the spike's reach, made it a versatile weapon in both offense and defense. The thumb spike's evolutionary origins are equally fascinating, representing a dramatic repurposing of a digit that in earlier dinosaurian ancestors served grasping or foraging functions. Its enlargement and sharp specialization underscore how natural selection favored effective defensive and social tools in agriculturally important herbivores. Additionally, iguanodonts often traveled and foraged in groups, which, when combined with the thumb spike's effectiveness, magnified their defensive capabilities. A mob of large, agile herbivores, each equipped with deadly thumb spikes, would have been a formidable obstacle for any predator. Fossil sites revealing bite marks on iguanodont bones, scars consistent with claw strikes, and evidence of healed wounds support a narrative where iguanodonts both suffered predation attempts and survived aggressive encounters, thanks in part to their evolutionary armament. In summary, giant iguanodonts and their iconic thumb spikes illustrate the sophisticated and active defense strategies that some herbivorous dinosaurs developed. Far from being passive grazers, these creatures leveraged anatomy and behavior to hold their own against predators and rivals alike, wielding their spiked thumbs as natural weapons in ancient battles. As we explore further adaptations, the armored nodosaurids await, walking fortresses employing an evolutionary suite of defensive innovations that offer a striking contrast and complement to the bite and slash tactics of iguanodonts. The story of herbivore defense continues to unfold with ever greater depth and complexity. In the pantheon of herbivorous dinosaurs, nodosaurids stand out as remarkable examples of evolutionary innovation in defense. Armored wonders whose rugged exteriors told tales of survival in a world filled with relentless carnivorous predators. Flourishing primarily in the late Jurassic, through the late Cretaceous periods. Nodosaurids were cousins to the ankylosaurids, but followed their own unique evolutionary path that emphasized passive defense through extensive body armor and spiked protrusions rather than tail clubs. In this chapter, we journey into the fascinating biology, defense strategies, and evolutionary significance of nodosaurids, revealing how these heavily fortified dinosaurs carved an enduring niche within their ecosystems. Nodosaurids were medium to large quadrupeds, sometimes reaching lengths of up to 7 meters, adorned from head to tail with thick osteoderms, bony plates embedded in their skin that served as a biological suit of armor. What distinguishes nodosaurids from their ankylosaurid relatives is the arrangement and specialization of their armor, which often included pronounced shoulder spikes, elongated spines, and an absence of the iconic tail club. Their bodies resembled moving fortresses, offering formidable protection against tooth and claw. The osteoderms varied widely in shape and size, forming mosaics of interlocking plates that provided both a shield and a deterrent. Many nodosaurids sported large, sharp spikes over the shoulders and sometimes along the sides of the body, creating a spiked barrier that predators had to navigate with extreme caution. These spikes could inflict painful wounds and complicate any pursuit, especially to attacking theropods accustomed to targeting flanks and vulnerable areas. Fossil evidence, including remarkably preserved specimens like Borealopelta from Alberta, showcases these defensive features with incredible clarity. Borealopelta's armor was so well preserved that scientists could observe the arrangement of osteoderms and even remnants of the dinosaur's original coloration. An unexpected discovery indicating a complex camouflage system with reddish-brown hues and countershading. This camouflage likely helped nodosaurids avoid detection, complementing their armor by preventing surprise attacks. The evolution of such defensive innovations is indicative of intense predation pressures in Cretaceous ecosystems. Nodosaurids' passive defense contrasted with more active defense mechanisms employed by ankylosaurids or horned ceratopsians. Instead of fighting back with tail clubs or large horns, nodosaurids relied on their impregnable armor and strategic use of their environment, adopting behaviors like remaining motionless and blending into surroundings to avoid conflict altogether. Beyond defense, the robust build and armor imposed metabolic and biomechanical constraints. Heavy armor increased energy requirements and limited speed and agility, signaling that nodosaurids evolved in niches where defense and stealth outweighed escape. Their legs were strong but short, supporting heavy weight but unsuited for rapid flight, making their armor and spiky protrusions essential for survival. Behaviorally, nodosaurids may have been solitary or lived in small groups, unlike the large herds seen in hadrosaurs. This lifestyle could coincide with their defensive strategy, relying on stealth, camouflage, and passive armor rather than group vigilance. Patterns of healed fossils and puncture wounds, matching theropod bite marks on nodosaurid bones, underscore the perpetual risk these animals faced. However, the extent of their armor and spikes undoubtedly gave them an edge in the evolutionary arms race, with predators forced to adapt or seek easier prey. In the story of the evolution of herbivore defenses, nodosaurids represent a masterclass in passive protection and evolutionary resilience. Their spiked armor and unique survival strategies broaden our understanding of how herbivores balanced vulnerability and strength in the Mesozoic. As we continue, the narrative beckons us to secretive yet surprisingly fierce members of the ornithopod family. Small but deadly creatures whose unexpected defense mechanisms challenge assumptions about size and danger, showcasing the marvelous diversity of dinosaur survival strategies. When we think about dangerous dinosaurs, the mind often conjures images of towering ceratopsians with their piercing horns, massive sauropods whose size alone guaranteed safety, or heavily armored ankylosaurids wielding lethal tail clubs. Yet, lurking in the shadows of paleontological history is an often underestimated group: the ornithopods. These seemingly modest and often smaller herbivores displayed surprising adaptations that made them highly dangerous in their own right. An evolutionarily successful combination of speed, agility, weaponry, and social behavior that enabled them to challenge predators and carve out unique niches. This chapter explores how these small but deadly ornithopods defied expectations and became formidable defenders on ancient Mesozoic battlefields. Ornithopods were a diverse group of herbivorous dinosaurs, spanning early forms like Hypsilophodon to the more familiar and substantial hadrosaurids, or duck-billed dinosaurs. While some grew large, many remained relatively small, nimble creatures ranging from 1 to 5 meters in length. Their moderate size enhanced maneuverability and speed, critical survival traits that allowed them to evade or outpace predators through agility rather than brute force. A defining feature that elevated ornithopods' defensive capabilities was their highly specialized limb and jaw anatomy. Their powerful hind limbs and lightweight skeletal structures provided rapid bipedal locomotion, enabling quick sprints and sharp turns. This locomotor skill increased their chance of escape, permitting them to exploit densely vegetated or complex terrains where predators might struggle. Fossilized footprints and trackways support the notion of varied speeds and dynamic mobility, including sudden burst movements when threatened. Beyond speed, many ornithopods evolved precision biting and chewing abilities that went beyond mere feeding efficiency. Their complex dental batteries, composed of hundreds of tightly packed teeth, allowed for effective processing of tough vegetation, and in some cases could be used to deliver painful bites against attackers, a rare but significant form of defense for herbivores. Remarkably, some ornithopods also developed physical weapons. The iguanodontians, for example, wielded bony thumb spikes that could be employed to slash or stab. More unexpectedly, some smaller ornithopods possessed stiffened tail structures and robust forelimbs, potentially used in combat or warding off threats. Paleontologists have found evidence of healed injuries and scars consistent with such interactions, underscoring their practical role in defense. Moreover, social behavior amplified the dangers ornithopods posed to predators. Many species exhibited herd behavior, traveling in large groups ranging from dozens to hundreds of individuals. Herding provided safety in numbers. The collective vigilance meant early detection of predators, coordinated alarm calls, and a defensive front challenging to breach. Some studies postulate complex communication systems involving vocalizations, body posturing, and possibly visual signals through crests or skin displays. In response, predators faced not isolated prey, but coordinated herds capable of swift movement and mutual protection. Fossilized nesting sites with multiple juvenile tracks hint at parental care behaviors, which would have entailed aggressive defense of vulnerable young, further elevating the group's overall defensive capabilities. This protective maternal or communal behavior likely escalated herbivore aggression when nests or offspring were threatened. Ecologically, the success of ornithopods in diverse habitats, from coastal floodplains to forested inland regions, illustrates their adaptability and survival acumen. Their combination of speed, defensive anatomy, weaponry, and social structures allowed them to occupy niches that demanded both agility and cooperative defense. In the grand theater of dinosaur evolution, the ornithopods redefine what it means to be dangerous. Their smaller size belied a lethal combination of traits, enabling them to survive or even repel some of the scariest predators of their time. They remind us that danger is not solely the province of towering giants or terrifying weapons, but can also be embedded in swiftness, intelligence, adaptability, and social cooperation. As we continue to explore the fascinating diversity of herbivorous dinosaur defenses, the next chapter will illuminate the power of collective defense. Flocks, herds, and the age-old adage that there is strength in numbers. Together, these themes paint a complex and rich map of survival strategies that echo through both ancient history and the natural world today. The phenomenon of group living, flocks, herds, and other collective assemblies, plays a profound role in the survival strategies of countless animal species, and herbivorous dinosaurs were no exception. In environments where lurking predators posed constant threats, the power of numbers became an evolutionary advantage, transforming what might otherwise be vulnerable individuals into a formidable force against attack. Understanding the dynamics of collective defense among herbivorous dinosaurs not only sheds light on their social structures, but also challenges the outdated portrayal of solitary, defenseless plant eaters. This chapter explores the evidence for such group behaviors, the mechanisms through which herding increased survival, and the evolutionary implications that shaped the most dangerous herbivorous dinosaurs. From the extensive fossil record, numerous mass death assemblages have been uncovered, where hundreds or even thousands of herbivorous dinosaur fossils are found in close proximity. These bone beds often include juveniles, adults, and even eggs, painting vivid pictures of herd living. Such evidence suggests that species like hadrosaurs, ceratopsians, and even some sauropods traveled and foraged in groups. The ecological benefits of collective behavior are manifold: safety in numbers, increased vigilance, and complex social interactions that enhanced defense against predation. One of the simplest yet most effective advantages of living in groups is the dilution effect. When many individuals cluster together, the likelihood of any single animal being targeted by a predator decreases. Predators hunting in environments full of dense herds must compete with distraction and confusion, reducing hunting efficiency. Additionally, the presence of many eyes and ears increases the probability of early predator detection. Several fossil trackways document coordination among herbivorous dinosaurs moving in parallel, likely indicating collective movement with sentinels or scouts alerting others to danger. Alarm calls, vocalizations, and visual signals were essential components of this collective vigilance. Studies of hadrosaur cranial crests suggest that these frontal resonating chambers may have been used to produce a variety of sounds, ranging from low-frequency booms to high-pitched alarms, capable of conveying specific information about threats or herd cohesion. Social communication not only facilitated defense, but also helped maintain the cohesion and safety of the group. Behaviorally, collective defense could manifest in several ways. In herds of ceratopsians, for example, individuals may have positioned the young or vulnerable members in the center, surrounded by adults acting as physical barriers and defenders. The impressive horns and frills of ceratopsians might have been marshaled collectively to deter predators, creating a daunting shield of spikes and bony armor. Similarly, hadrosaurs could have used speed and maneuverability as a collective, a moving wall capable of outpacing threats. Fossilized nesting sites further support the idea that many herbivorous dinosaurs invested in parental care and communal protection of offspring. The defense of nests against predators required coordinated vigilance and aggressive responses, further intensifying intraspecific social bonds that underpinned collective defense. The evolutionary stakes for group living were high. Individuals in herds benefited from increased survival, but at the cost of resource competition and increased disease transmission. These trade-offs underscore the delicate balance that shaped the social lives of dinosaurs, driving behaviors that optimized defense without compromising other vital needs. Collective defense also influenced predator-prey dynamics, compelling carnivores to develop new hunting tactics, such as ambush techniques or targeting solitary individuals. This continuous interplay contributed to the escalating arms race that produced the elaborate defenses and behaviors we observe in the fossil record. In some, flocks, herds, and other forms of collective defense elevated herbivorous dinosaurs from isolated food sources to powerful, coordinated communities. Their social structures, communication, and coordinated behavior made them dangerous adversaries to predators, redefining our understanding of herbivore survival. As we progress to examine the remarkable herbivores of Gondwana in the southern hemisphere, we will discover how unique environmental pressures and evolutionary histories produced a fascinating array of dangerous plant-eating dinosaurs, further enriching the tapestry of Mesozoic life. The Mesozoic world was not uniform. It was a mosaic of continents, each sculpting unique environments and biological communities. The southern supercontinent, Gondwana, comprising present-day South America, Africa, Antarctica, Australia, and the Indian subcontinent, hosted a distinctive assembly of herbivorous dinosaurs whose adaptations and behaviors illustrate an equally compelling story of danger and survival. These southern dwellers, shaped by the distinct climates, flora, and evolutionary pressures of Gondwana, contributed remarkable chapters to the saga of herbivorous dinosaur defenses. This section surveys these extraordinary creatures, uncovering their unique strategies amid the shifting landscapes of the southern hemisphere. One of the most notable groups of Gondwanan herbivores were the titanosaurs, a diverse clade of sauropods that included some of the largest land animals ever to walk the earth. Unlike their northern cousins with well-studied long whip-like tails or distinctive armor, many titanosaurs evolved broad, robust bodies swathed in osteoderms, bony deposits embedded in their skin that offered passive protection. Species like Saltosaurus from Argentina exemplify this armored gigantism, equipped with pebble-like osteoderms and spikes, reducing vulnerability to large predators like ankylosaurids and carcharodontosaurids dominating southern faunas. Beyond armor, Gondwanan herbivores showcased other remarkable adaptations. The abelosaurid-dominated predator guilds of Gondwana exerted immense pressure, leading herbivorous species to evolve defensive features tailored to their unique threats. For instance, the diverse and robust nodosaurid relatives present in Antarctica and Australia developed specialized armor suited to harsh climates and predation. Another spectacular Gondwanan herbivore group are the iguanodontians, including genera like Muttaburrasaurus from Australia. These medium to large ornithopods wielded robust forelimbs and often displayed bony cranial features possibly related to social signaling or defense. Fossil sites suggest some species might have engaged in herd behavior, while their morphology indicates a capacity for both speed and physical defense, allowing them to thrive amid predators specialized for ambush and endurance hunting. Ceratosaur-dominated predators, characterized by robust but relatively limited cursorial capacities, shaped herbivore defensive strategies differently. Many southern ornithischians evolved close-range defense tactics such as strong jaws, claws, and physical displays designed for intimidation, avoiding protracted chases. This pressure is evident in the anatomical diversity and distinctive defensive morphologies that differ markedly from their northern hemisphere counterparts. Intriguingly, some Gondwanan herbivores, like the enigmatic and heavily built Chilosaurus, occupy puzzle pieces within this narrative. Such dinosaurs demonstrate unique evolutionary experiments, combining traits of large-bodied herbivores with agile, sometimes carnivore-like characteristics, showcasing the fluidity of adaptation in Gondwana's isolated, diverse ecosystems. Environmental factors further influenced these adaptations. Fluctuating climates, varying vegetation types, and changing geographic isolation prompted rapid evolutionary responses. Sparse fossil evidence from Antarctica reveals that even in colder, extreme environments, herbivorous dinosaurs maintained developed defenses, highlighting their resilience and adaptability. Fossil trackways and bone beds from Gondwanan sites provide evidence of social aggregation, reinforcing the importance of group living as a defensive tactic. Large gatherings of herbivores would have complicated hunting by predators and facilitated communal vigilance, necessary in ecosystems marked by both predator diversity and environmental challenges. Collectively, these powerful southern herbivores embodied strategies that were as innovative as they were effective. Their evolutionary responses to the unique dynamics of Gondwana underscore the complexity of Mesozoic herbivore survival, expanding our global perspective on dinosaur defense. As we proceed into topics exploring the role of parental care and nest defense in herbivorous dinosaur aggression, the dynamic and diverse legacy of Gondwana's giant plant eaters will serve as a meaningful backdrop. Their stories remind us that danger and defense are universal themes threaded through the tapestry of dinosaur evolution, transcending continents and climate zones alike. In the vast expanse of the Mesozoic era, the survival of herbivorous dinosaurs hinged not only on their physical adaptations, like horns, armor, or speed, but also on sophisticated behaviors that enhanced the protection of the next generation. Parental care and nest defense played crucial roles in shaping aggressive behaviors within herbivorous dinosaur species, adding a social and emotional dimension to the defensive arsenal beyond mere anatomy. This chapter explores how nurturing instincts and protective strategies fostered aggression and defense among plant eaters, influencing their evolution and interactions with predators and conspecific rivals alike. Evidence for parental care in herbivorous dinosaurs comes from remarkable fossil discoveries of nesting sites and juvenile remains. Large nesting colonies, such as those attributed to hadrosaurs and certain ceratopsians, reveal a strategy of communal nesting and extended care. Fossils show nests containing eggs, embryos, and hatchlings at various development stages, often alongside traces of adults nearby. Such proximity implies not only protection of nests from predators, but continual parental involvement in guarding, nurturing, and possibly guiding young dinosaurs as they matured. Nest defense naturally provoked aggression. Vulnerable eggs and hatchlings were prime targets for predators seeking easy meals, prompting adults to exhibit patterns of alertness and active defense. The presence of formidable herbivore weaponry, horns, spikes, bony frills, took on heightened significance in this context. These structures were wielded not just against predators, but potentially in social displays or violent encounters during attempts to safeguard nests. Direct fossil evidence supports this dynamic, with adult dinosaurs showing healed injuries consistent with combats around nesting grounds. In ceratopsians, for instance, scarring and horn damage demonstrate that battles occurred, likely territorial or protective in nature, where defense of reproductive grounds could escalate to enforced aggression. When resources like nesting sites or food were contested, conflicts between rivals could heighten, further contributing to aggressive behavior patterns. Additionally, juvenile dinosaurs were not merely passive recipients of care, but influenced social structures and group dynamics. Protection of young could encourage herding behavior, increasing the power and coordination of the group as a whole. Such sociality enhanced both the defense of offspring and collective vigilance against predators. Parental aggression also had evolutionary implications, potentially accelerating the development and refinement of defensive morphologies. Species with more effective parental defense fostered greater offspring survival, selecting for stronger weaponry, more aggressive temperaments, and cooperative behaviors. This interplay of biology and behavior represents a feedback loop crucial to the success of many herbivorous lineages. Beyond physical defense, vocalizations and complex communication likely augmented parental protection tactics. Fossil evidence of specialized cranial crests in hadrosaurs, which may have functioned as resonating chambers, suggests an ability to produce warning calls or signals within a group, alerting other members to danger and summoning coordinated defense efforts. Ultimately, parental care and nest defense transformed herbivorous dinosaurs from solitary grazers to socially complex animals exhibiting aggressive, protective behaviors that rivaled their physical defenses. The stakes of survival extended beyond individual longevity to the perpetuation of family lines, enhancing the evolutionary pressure on herbivores to develop not only anatomical but behavioral weapons. As we transition to examine the fierce rivalries and clashes between herbivores themselves in the next chapter, understanding the role of parental aggression provides critical context. The protection of kin, territory, and resources drives much of the conflict that shaped the dinosaurs' evolutionary journey, revealing herbivores as active, sometimes violent agents in their ecological narratives, rather than passive giants beaten solely by predation. In the vast prehistoric landscapes of the Mesozoic, the dominant narrative often centers on the ferocious battles between towering predators and their herbivorous prey. Yet, beneath the surface of this dynamic predation drama lies an equally compelling, yet less often examined story. The intense rivalries and territorial disputes fought not between predator and prey, but among herbivores themselves. These clashing titans, herbivorous dinosaurs pitted against each other in contests of strength, dominance, and survival, reveal a fascinating dimension of dinosaur behavior that highlights their complexity and fierceness beyond simple grazing. This chapter explores the evidence and implications of herbivore versus herbivore battles, offering a new perspective on how these creatures defended not only themselves, but also territories, mates, and social hierarchies. Territoriality and rivalry are well-recognized behaviors in modern animals and have long been hypothesized for dinosaurs. For herbivorous dinosaurs that relied on large, resource-rich areas for feeding and reproduction, defending a territory, or at least access to key resources, was essential. Fossil evidence, combined with anatomical and biomechanical studies, supports the reality that many herbivores engaged in direct confrontations, utilizing their unique anatomical armaments as weapons in these contests. The ceratopsians are a prime example, with their massive skulls adorned by formidable horns and frills, evolving not just for predator deterrence, but also for intraspecific combat. Fossil skulls bear scars, punctures, and healed injuries that indicate clashes between individuals wielding their horns against one another. These battles, although potentially risky, allowed individuals to establish dominance, secure mating rights, or control territory. The presence of different horn morphologies among chasmosaurines and centrosaurines also suggests a role in species recognition and sexual selection, where horn size and shape communicated strength and fitness. Similarly, pachycephalosaurs provide compelling evidence of head-to-head combat. Their thick, domed skulls, sometimes reinforced with spikes, are hypothesized to have been used in headbutting or flank-butting competitions. Biomechanical models indicate that these animals could sustain and deliver impactful blows, and fossilized injuries on their domes are consistent with repeated combat encounters. Even ankylosaurids and nodosaurids, commonly regarded as passive, armored herbivores, may have engaged in territorial or dominance disputes. While their primary defense mechanism involved passive protection, the ankylosaurid tail club could also serve offensive purposes, possibly in clashes with rivals. Shoulder spikes seen in notosaurids could have been used in agonistic displays or combat, marking another avenue where physical defenses contributing to predator survival doubled as weapons in herbivore rivalries. Hadrosaurs, known for their size and pack behavior, likely competed for territory and mates as well. Though lacking prominent horns or clubs, some species developed elaborate cranial crests that may have functioned in visual and acoustic displays, established hierarchies, and perhaps diffused the need for violent encounters. Nevertheless, fossil evidence of injuries and potential bite marks imply that disputes could escalate to physical confrontations. The complex social structures that such rivalries imply required behavioral sophistication. Ritualized combat, where displays, posturing, and controlled skirmishes minimize fatal outcomes, would have been an evolutionary advantage. This behavior mirrors modern horned and antlered mammals, where dominance is established through relatively non-lethal combat rituals, conserving individuals while determining social status. Territorial battles also held profound evolutionary consequences. The pressures of maintaining or expanding territories likely drove the diversification of defensive adaptations, fueling the development of more elaborate horns, stronger frills, thicker dome skulls, and more effective tail weapons. The arms race extended beyond predator-prey interactions and permeated herbivore behavioral ecology. Fossilized bone beds capturing multiple individuals with similar injuries, sometimes alongside evidence of agonistic behavior, offer snapshots of these titanic clashes. They vividly capture the perilous balance these herbivores maintained between cooperation, necessary for survival, and fierce competition that defined their hierarchical societies. Ultimately, the clashing titans of herbivorous dinosaurs illuminate an evolutionary landscape where aggression and defense were not only reactions to outside threats, but integral parts of social and reproductive strategies. These confrontations shaped the anatomy, behavior, and survival of herbivorous dinosaurs, demonstrating that danger lurked not only in the jaws of predators, but also in the battles waged among the herbivores themselves. As we move to explore situations where herbivores rose to apex defender roles and even became predators' prey, the insights gained here will deepen our understanding of the complex web of survival and the unexpected ferocity that characterized the lives of these ancient giants. In the grand theater of the Mesozoic ecosystems, herbivorous dinosaurs were often portrayed as passive targets, marked for predation by the voracious carnivores that roamed ancient landscapes. However, a closer examination reveals a more nuanced and astonishing reality. There were moments and circumstances when these plant eaters transcended their traditional roles, turning the tables to become apex defenders, or even transforming predatory threats into their own prey. This remarkable shift challenges the simple predator-prey dichotomy and highlights the evolutionary ingenuity and power encapsulated in the most dangerous herbivorous dinosaurs. A critical factor in this transformation was often the sheer size and physical weaponry that certain herbivore species wielded. Massive ceratopsians like Triceratops, heavily armored ankylosaurids, and the gigantic sauropods not only presented formidable obstacles, but in some cases were capable of directly inflicting mortal wounds on predators. Tooth marks on the bones of tyrannosaurids, for example, have been found that match defensive wounds likely delivered by the tail clubs or horned skulls of their herbivorous adversaries. Such injuries suggest that attempts to subdue large herbivores could prove deadly to predators, highlighting the physical risks involved in hunting these prey species. Close encounters between herbivores and predators could easily shift in favor of the former. Ankylosaurids, known as the living tanks of the Jurassic and Cretaceous, employed their massive tail clubs with astonishing power. Biomechanical analyses suggest that a single strike could cause fractures or serious trauma, not just dissuading predators, but potentially killing them outright. Historical analogues in modern nature, such as large mammals capable of fatally injuring their attackers, underscore the plausibility of such lethal herbivore defenses in the dinosaurian past. Moreover, predator behavior considered the formidable defensive abilities of herbivorous dinosaurs. Predators often preferred attacking juveniles or sick individuals, recognizing that mature adults posed serious risks. Some fossil evidence shows predators abandoning kills or prey unconsumed due to defensive retaliation or injury risk, a direct testament to how aggressive herbivores could turn the tables in combat. Social behavior amplified this dynamic. Herding herbivores could collectively fend off carnivores by forming defensive formations, such as rings with vulnerable juveniles at the center and aggressive adults on the perimeter brandishing horns, spikes, or tail clubs. Coordinated defense increases the chance of injuring predators and deterring attacks, effectively elevating the herbivore group to apex defender status within their habitat. The rarity of herbivores successfully turning predators into prey in fossil records likely owes to preservation biases and the episodic nature of such encounters. Nonetheless, these moments profoundly influenced the predator-prey evolutionary arms race. Defensive innovations in herbivores pressured carnivores to develop enhanced strategies, sharper teeth, better hunting techniques, and social hunting tactics. Each adaptation sometimes counterbalanced by new or improved herbivore defenses. In the larger ecological context, the capacity of herbivores to become apex defenders contributed to ecosystem balance, preventing unchecked carnivore dominance and fostering biodiversity. This balance reinforced natural checks and promoted continuous evolutionary innovation on all sides. Herbivorous dinosaurs thus emerge as complex agents in their environments, capable not only of survival, but of active defense, transforming predatory attacks into fatal errors. Their evolution reflects resilience, power, and an extraordinary capacity to shape their world. In the following chapter, we will shift perspective to consider the human fascination with these creatures, how paleontology and popular culture have intersected to shape our understanding of these dangerous giants, and how modern depictions influence our perceptions of dinosaur life. The story of herbivorous dinosaurs is not confined to the pages of scientific journals or the depths of the fossil record. It also unfolds vibrantly in the human imagination, bridging the realms of paleontology and popular culture. The way humans have encountered, interpreted, and depicted these ancient creatures profoundly shapes our understanding of their nature. From the realization that herbivores were not simply passive, gentle giants, to perceptions of them as complex, sometimes dangerous, beings with elaborate defense strategies. This chapter explores the dual lens of scientific discovery and cultural representation, revealing how the interplay between the two has advanced and complicated our views of these prehistoric herbivores. The dawn of modern paleontology in the 19th century brought with it awe-inspiring revelations. Enormous bones, towering skeletons, and fossilized remains that hinted at creatures unlike any living today. Early scientific interpretations often cast herbivorous dinosaurs as massive, slow-moving, and defenseless, reflecting both the limited evidence available and the influence of contemporary notions about large herbivores, often analogized to modern elephants or rhinoceroses. This concept of gentle giants permeated early museum exhibits, scientific literature, and public consciousness. However, as fossil discoveries multiplied and research techniques evolved, paleontologists uncovered signs that herbivorous dinosaurs were far from helpless. Evidence of complex horned frills, armor plating, tail clubs, and even healed injuries indicative of combat highlighted a reality of defense, aggression, and social complexity. Scientific consensus began to shift. Herbivores were no longer mere victims, but active players in their ecosystems, armed and ready to defend. These revelations increasingly filtered into popular culture, influencing how herbivorous dinosaurs were portrayed in books, films, and media. Early cinematic depictions, such as those in the 1933 film King Kong, presented dinosaurs as monstrous creatures, though often with a carnivore-centric focus. Subsequent portrayals in the mid to late 20th century, especially in landmark films like Jurassic Park, balanced the narrative. Herbivores like Triceratops and Stegosaurus were shown as massive and awe-inspiring, but also capable of defending themselves fiercely when provoked. The popular imagination embraced and expanded the image of dangerous herbivores, cementing their roles as not just prey, but powerful defenders. Educational programming, documentaries, and children's literature further reinforced these views, while the advent of digital animation allowed for dynamic, realistic portrayals of their behavior, including defensive posturing and combat. Nevertheless, cultural portrayals sometimes oscillate between scientific accuracy and dramatic license, shaping public perception with both education and entertainment. For instance, certain media exaggerate the aggressiveness of herbivores for thrilling storytelling, while others emphasize peaceful, majestic qualities, perpetuating the myth of gentleness. These varied depictions contribute to a cultural mosaic reflecting the complexities of translating scientific findings into accessible narratives. Moreover, the fascination with dangerous herbivorous dinosaurs has inspired a wide range of human responses, from scientific research and museum exhibitions to artistic works, and even the naming of sports teams and commercial brands. This cultural integration underscores the profound impact these ancient giants have had on human creativity and identity. On the scientific front, ongoing discoveries, such as fossilized skin impressions, trackway evidence of herd behavior, and biomechanical analyses, continuously refine our understanding, challenging popular stereotypes and encouraging updated portrayals. The dialogue between paleontology and popular culture thus remains dynamic, fueled by new findings and evolving interpretations. Importantly, public engagement with their stories fosters broader interest in natural history, evolution, and conservation. By appreciating herbivorous dinosaurs as dangerous, complex creatures, audiences gain insight into the intricacies of life's evolutionary arms races and the fragile balance within ecosystems. In summary, the human perspective on dangerous herbivorous dinosaurs reflects a journey from simplistic stereotypes to richly textured understanding. Through the twin lenses of scientific inquiry and cultural imagination, these ancient plant eaters continue to captivate and educate, inviting us into a prehistoric world where survival depended on strength, cunning, and resilience. As we move forward, the legacy of these herbivores, how their adaptations live on in modern animals, awaits exploration, linking the distant past with the living present in a continuing story of evolution and survival. The legacy of the dangerous herbivorous dinosaurs extends far beyond their extinction some 66 million years ago. It echoes through the anatomy, behavior, and survival strategies of modern animals that inherit the evolutionary triumphs forged during the Mesozoic era. Their formidable adaptations, whether in the form of defensive weaponry, social behaviors, or sheer size, have left indelible marks that continue to influence how herbivores today face threats and navigate complex ecological interactions. This chapter explores how the remarkable defense strategies of prehistoric herbivores resonate in the living world, offering a profound testament to the enduring power of evolutionary innovation. One of the most direct legacies is found in the bony armor and spikes adorning the bodies of modern reptiles and mammals. Armadillos, for instance, with their protective, segmented armor, reflect a distant echo of the osteoderms seen in nodosaurids and ankylosaurids. While differing in structure and composition, the functional convergence is clear: a mobile fortress against predators. Similarly, modern porcupines wield quills as deterrents, visually analogous to the spiny defenses of some ceratopsians and stegosaurs, underscoring how intimidation and painful physical deterrents remain powerful survival tools. Horns and antlers, widely exhibited in mammals such as deer, bison, and goats, demonstrate a particularly vivid continuation of Mesozoic traits. The cranial weaponry that characterized horned dinosaurs, ceratopsians being the prime example, finds parallels in these structures used for combat, defense, and social signaling. The ritualized clashes and dominance displays in modern species recall the head-butting and horn-locking behaviors inferred from fossil evidence, illustrating deep evolutionary continuities in managing aggression and competition. Massive size as a defense mechanism also persists. Elephants, the largest terrestrial mammals today, embody principles seen in sauropods, leveraging bulk and strength to deter predators. Their formidable tusks serve multiple roles, from feeding tools to weapons in intraspecific conflicts and predator deterrence, mirroring the multifunctionality inherent in many dinosaurian defenses. The strategic use of size extends not only to physical obstruction of predators, but also to influence ecological landscapes, reminiscent of the ecosystem engineering practiced by sauropods. Beyond physical adaptations, social behaviors such as herding and collective defense remain crucial strategies. Many modern herbivores form groups that provide increased vigilance and protection, directly paralleling the herding and flocking behaviors reconstructed for hadrosaurs, ceratopsians, and other dinosaurs. Alarm calls, coordinated movements, and protective positioning within herds continue the evolutionary playbook established millennia ago for reducing predation risk through unity and communication. Parental care and nest defense, essential factors in herbivorous dinosaur aggression, are well represented among present-day species as well. From ground-dwelling birds fiercely guarding their nests to mammals exhibiting nurturing behaviors that sometimes escalate into aggressive defense of offspring. These behaviors reflect deeply rooted evolutionary imperatives centered on reproductive success and survival. Intriguingly, evolutionary biology reveals that some defensive traits apparent in modern species may have roots traceable to non-avian dinosaurs. Birds, the direct descendants of theropod dinosaurs, possess a suite of defensive and social behaviors that echo their extinct relatives' strategies. Even though birds are mostly omnivorous or carnivorous, their complex social dynamics, communication systems, and predator avoidance tactics showcase the behavioral heritage of their prehistoric ancestors. Moreover, the evolutionary arms race that drove the diversification of herbivore defenses has shaped predator species as well, fostering adaptability and complexity across ecosystems. This co-evolutionary dance underscores the interconnectedness of life, where the innovations of one group influence the trajectory of many. The legacy of dangerous herbivorous dinosaurs is, therefore, a living heritage, a continual thread that weaves through natural history into the present, enriching the diversity and resilience of life. Their adaptations teach us about the power of evolution, the balance of ecosystems, and the nuanced strategies life employs to survive in a world fraught with danger. As we approach the concluding chapters, we will reconstruct dramatic encounters between these ancient giants, bringing to life the fierce realities they faced and the remarkable ecological theater in which they lived. Through these stories, the lessons of evolution and survival embodied by the most dangerous herbivorous dinosaurs resonate, reminding us of nature's relentless creative force. Imagine a warm, humid day in the late Cretaceous period, roughly 70 million years ago, on the floodplains of what is now North America. The dense vegetation bows gently in a light breeze, the air humming with the distant calls of ancient creatures. Here, among towering conifers and ferns, a herd of Triceratops grazes peacefully, occasionally flicking their tails and exchanging low, guttural grunts to maintain social bonds. These massive herbivores sport formidable three-horned faces crowned with protective frills, built not only for feeding efficiency, but also for defense. As midday approaches, the herd's calm is disrupted. The ground vibrates with the heavy footfalls of a large Tyrannosaurus rex, a terrifying predator and apex carnivore of this time. From the edges of the forest, the tyrant lumbers silently yet purposefully, eyeing the herd with predatory intent. The dynamics between predator and prey have played out over millennia, etched in their mutual adaptations and behaviors. Within the herd, wariness sharpens rapidly. The largest males position themselves protectively around the younger, smaller individuals. The herd instinctively tightens, the adults forming a shield while the juveniles move toward the center. A resonant bellow escapes from the lead male, possibly a warning or a rallying call, reverberating through the trees. Nearby, a group of hadrosaurs, their reminder of speed and social survival strategies, bound away toward open plains, alerted by the predator's presence. The tyrannosaur prowls closer, testing the herd's resolve. Sensing this, a Triceratops male lowers his massive head, already brandishing his prominent brow horns as weapons. The predator makes a feint, seeking an opening, but the defender swings its head with calculated force. The two giants clash, the Tyrannosaur's jaws snapping inches from the defender's armored forehead. The Triceratops counters with a powerful thrust from its horns, catching the predator and driving it back. Nearby, an ankylosaurid, adorned with heavy armor and a swinging tail club, senses the disturbance and stomps toward the fray. The ankylosaurid swings its bony tail decisively, cracking it against a fallen log, but hinting clearly at its capacity to strike predators with bone-crushing force. The predator momentarily hesitates, wary of further injury. The battle escalates, a blur of dust, roaring challenges, and defensive posturing. The Triceratops herd pushes forward, coordinated yet instinctive, while the Tyrannosaur evaluates the risk, seeking vulnerable targets. Finally, recognizing the dangers posed by the united and well-armed herd, the predator retreats toward the forest edge, stalking anew under the cover of shadows. As quiet returns, the Triceratops herd disperses, the tension releasing like breath after a storm. The survivors graze once more with renewed caution, their physical and social defenses having secured another day. Their horns, armor, size, and collective vigilance made them not mere victims, but warriors in their own right, shaping the evolutionary arms race that defines this primordial world. This dramatic encounter exemplifies the daily reality for many herbivorous dinosaurs, where survival depended not only on ancient titans' physical might, but also on social strategies, defensive innovations, and an ever-watchful eye for danger. It is within these ancient battlefields that the most dangerous herbivores carved their legacy, reminding us of the complexity, resilience, and unyielding spirit that defined their reign on Earth. As we conclude our journey through the world of the most dangerous herbivorous dinosaurs, we are left with profound insights into the powerful interplay between evolution, survival, and adaptation. These remarkable creatures, often overshadowed by the predatory dinosaurs in popular imagination, reveal a rich tapestry of biological innovation and resilience that challenges simplistic stereotypes of herbivores as gentle, passive giants. The diversity of defense strategies exhibited by herbivorous dinosaurs, from bone-crushing tail clubs of ankylosaurids and the triple-horned frills of ceratopsians, to the swinging thagomizers of stegosaurs and the razor-sharp thumb spikes of iguanodonts, demonstrates evolution's relentless creativity. Each adaptation arose in response to environmental pressures and the perpetual arms race with predators, as well as intraspecific competition and social dynamics. This reveals survival not just as a matter of raw strength, but as a multifaceted negotiation involving anatomy, behavior, ecology, and even sociality. Moreover, the fossil and behavioral evidence reveals herbivores as active participants in their ecosystems, capable of aggression, defense, and complex social interactions. The evolution of such traits indicates that surviving in a world brimming with danger required more than just size or speed. It demanded versatility, strategy, and sometimes formidable weaponry. These lessons transcend the ancient past, resonating with modern biological principles, that survival is not solely the domain of predators, but a dynamic dance involving all life forms. The adaptive ingenuity of herbivorous dinosaurs underscores the interconnectedness of species and the powerful effects of ecological relationships driving evolution. Their story also illustrates the value of looking beyond preconceived notions and stereotypes. In recognizing the dangerous capabilities and resilience of herbivorous dinosaurs, we gain a deeper appreciation for the complexity of evolution, the balance of ecosystems, and the relentless drive of life to innovate and persist. As we reflect on these ancient giants and their legacies visible in today's natural world, we are reminded that survival is multifaceted, shaped by an array of forces both physical and behavioral. The dangerous herbivores of the Mesozoic teach us that evolution is not a simple tale of predator versus prey, but a grand narrative of mutual influence, adaptation, and survival against all odds. In contemplating this, we embrace a richer, more nuanced understanding of the past and present, inspired by the resilience and power of these extraordinary creatures. Their legacy challenges us to continue exploring, questioning, and marveling at the wondrous complexity of life throughout Earth's history.